Hello, my name is Robbie, and today we will be talking about the physics of magnets.
To start off this discussion, let's first talk about what a magnet is. A magnet is a piece of iron or material that has its component atoms so ordered that the material exhibits properties of magnetism, such as attracting other iron-containing objects or aligning itself in an external magnetic field. This leads into our first topic about the causes of magnetism. So in order for a material to become magnetized, you must further look into the arrangement of the material's electrons. A substance that is not magnetic has electrons that spin in opposite directions, and this motion cancels out their magnetism. When an object becomes magnetized, their electrons spin in the same directions, which makes the object magnetic. Then, when the magnetized material is brought near another magnet, the north and south poles, which are where the magnetic force is the strongest within a magnet, are paired with another opposite-ended pole, so north would pair with south and vice versa. They would then come together and stick. Here in this video clip, we will see two magnets who are coming together at their opposite ends where the magnetic field is the strongest, and then when the alike poles are brought close, they then repel each other.
To show how strong they are, we'll just bring it together and see what happens. It's going to push it away from quite a distance. Anyway, we want it to be attracting, so I'm going to put it in that mode there when it's going to come towards us.
Magnets are also found everywhere in our daily life. We even happen to live on one. Earth happens to be one giant magnet with a massive magnetic field. But what is a magnetic field, you may ask? Well, I'll tell you. A magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. As previously mentioned, magnetic fields have a north and south point, with its largest strength being the greatest at each pole of the magnet. This was tested and seen in a lab we conducted when looking at the strength of magnetic fields with iron shavings as shown in the picture. Now, one of the biggest magnetic fields comes from our planet Earth. Earth's magnetic field comes from having an inner iron, nickel, and other small quantities of metal in the core, and since there is a lower pressure in the core, the metals are fluid. This flow of liquid iron and other metals swirl in whirlpools, creating electric currents that produce magnetic fields. This magnetic field benefits us living on Earth by protecting us with a magnetic shield that blocks the sun's deadly radiation. Without this shield, the solar wind would blow our atmosphere away, and then the liquid water would be unable to exist as it would be vaporized away. Here we can visually see the Earth's magnetic field and a huge bonus it gives us as it protects us from harm.
Our sun is constantly hurling deadly radiation out towards us. Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. If there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
On another note, a daily magnet everyone uses is a compass. A compass is an instrument containing a magnetized pointer that shows the direction of magnetic north and bearings from it. A compass's main use is for navigation and traveling, as it points in the direction you want to go. A compass has a magnet balanced in the middle at a pivot point, also known as the needle of the compass. However, the basis of the compass starts with the Earth's magnet. The needle of the compass interacts with the Earth's magnet, and since opposite poles attract, the north end of the needle points south and the south end of the needle points north, which is the one we follow when dealing with directions. Not only are magnets used for daily tasks like swiping credit cards and directions, but it is also used in wires. Physicists use the well-known right-hand rule to figure out the magnetic field, speed of the proton or electron, and the magnetic force of the thing they are testing. Many physicists and electricians use this rule when using wires and dealing with currents. In the photo shown, the equation F equals QVB sine theta represents Q the charge, V the speed of the proton or electron, and B the magnetic force, and sine theta the angle. All of these are to find the magnetic force. When dealing with current in a wire, we're talking about the way the positive charges move through a wire. Since we know that the current is just moving charges, the wire will also be affected by a magnetic field in the same way as a single moving charge, but only when there is a current passing through it. In wires, we can find this when using the right-hand rule. The magnetic field is made by a current in a straight wire that curls around the wire in a ring. You can find it by pointing your thumb in the direction of the current in the wire and curling your fingers. Your fingers will be curled in the same direction as the magnetic field around the wire. But if you already know the direction of the magnetic field, point your thumb in the direction of the magnetic field this time and curl your fingers just as before. This time, the circular direction of your fingers tells you the direction of the current that creates the magnetic field. And that's all we have for today.
And that concludes our video about magnets. Thanks for watching.